All right, good day, everybody. Welcome to our exciting episode of our YouTube tutorials. And we're seeing a very interesting series, which is the organic chemistry series. We're going to be looking at organic chemistry, but today, the topic in organic chemistry or the aspect of organic chemistry I'm going to be looking at is the beginning of aromatic chemistry, which is benzene and basic principles of benzene and some of the reactions it can undergo. Okay, it's a very unique compound of great importance and of great disadvantage to humanity. So benzene. So look at benzene. Okay, benzene actually. So I'll call it benzene and its compound. Benzene and its compound, or benzene and its reaction. Anyhow, we're going to look at it. So benzene was first discovered as an illuminating gas by a physicist known as Michael Faraday. So in 1825, Michael Faraday discovered benzene as an illuminating gas which was obtained from coal. Okay, he was trying to produce electricity from coal and got a gas that can illuminate light, which was benzene, which can burn to produce light. The gas could burn to produce light. That gas was benzene. So benzene was discovered by Michael Faraday in 1825. Later on, the first scientist to actually derive benzene from coal was around 1845, if I'm very precise, around 1845. His name is Hoffman. Hoffman. So Hoffman was the first scientist to obtain or derive benzene from coal. He synthesized benzene from coal in 1845. That was 20 years after Michael Faraday said such compound could exist. Okay, many did not take account to this compound as at this time they didn't know that it was going to be the foundation of aromaticity of organic compounds, or this is the first aromatic compound. They didn't know they just discovered the first aromatic compound, but these guys did a lot of research in benzene. Okay, then later on in 1865, when the benzene or the aromatic chemistry has grown to a little bit, to a great extent, around 1865, a man known as August Kekule, yeah, August Kekule observed benzene and said this compound, so he observed this compound already discovered by this guy and said this compound is aromatic and it is unique. Kekule, unfortunately, in his sad story, said he saw the structure of benzene in his dream to be a snake in which the head was touching its tail, arranged like this. Yes, the head was touching its tail, it was arranged like this. So Kekule said, this is the structure of benzene. Funny from dream. Though he did some experiment that proved this very correct, he tried to explain it, especially later when a man known as Ockel provided the foundation of aromaticity and said, for you to be an aromatic compound, you must be this, and this structure obeyed that Ockel's rule. Okay, it was so funny by story, but this guy is taking the full credit. But not only he discovered the structure of benzene, the structure of benzene was also first talked about by a man known as Joseph Joseph Leo Smith. Both Joseph Leo Smith and Augustus Kekule, they were both German. So Joseph Leo Smith in 1861. So 1861, Joseph Leo Smith suggested the structure of benzene, which was 100% inaccurate. So the first authentic structure of benzene was given by Kekule. Now, later on, two other scientists tried to talk about the structure of benzene, and they include Klaus and Dewar. So there's a scientist called Klaus and there's one called Dewar. Okay, they tried to explain the structure of benzene, and funny enough, their structure of benzene obeyed the formula C6H6. This is the condition. So we already know that. Okay, using some studies earlier, we already knew that the formulas of benzene is now C6H6. Okay, they could tell it was C6H6. So they were looking for a structure that will suit it. All right. So looking for a structure that will suit it. This structure by Dewar in around 1867, and this structure by Klaus. Okay, Klaus gave us this structure for benzene. Okay, it was a closed ring structure, and this structure by Klaus all explained the C6H6. So this was Klaus. So these three guys, Kekule structure, Dewa structure, class structure, they were very accurate for benzene. Yes, these structures were so accurate. They were accurate structure for benzene. But with time, as time will go on, as science will become very broadened, Kekule's structure tend to outshine these guys, tend to answer the correct answers, or tend to give us the, tends to obey all the provided rule for an aromatic compound. So this one explain almost all the question asked about this compound called benzene than these ones. So though these structures were, these were the earliest form of structure. So the earliest structure of benzene were given by Kekule, Smith, Dewa, and Klaus. Dewa and Klaus were around 1867. Great guys. They did the good experiment and they tried on bots. Now, but today in chemistry, they said today in chemistry, many scientists said the ratio of contribution of benzene structure was around 2:1:7. So they said Kekule structure, Dewa structure, and class structure, how they contribute to the modern structure of benzene is 2:1:7 on modern research. Okay, so these guys have a lot. This structure tells us a lot, but I cannot explain in this video. I have to be fast as possible. So, all right, so it tells us a lot for the structure of benzene. Class also tells us a lot for the structure of benzene, but we have to be fast as possible. Okay, now after all said and done, still on the structure of benzene, a man known as Linus Pauling talked about using, haven't did a research on aromatic compounds. Linus Pauling did something strange for benzene, something very strange. Pauling said that all the structures of benzene, many were correct, and he can explain the original structure of benzene. Now, before I move further, before I explain the structure of benzene, I would like to talk about Hooke's rule very fast. Now, a man known as Hooke's provided a rule that any aromatic compound should have 4n plus 2 pi delocalized electron. So, an aromatic compound should have 4n plus 2 pi delocalized electron, and the compound should have a ring. Now, that brings us to Kekule's structure, which was earlier discovered. Now, according to Kekule, this is the structure for benzene. If you are a good chemist, you will call this cyclohexatriene. This was the structure of benzene according to Kekule. So we have double bond alternating single bonds. Yes, according to Kekule, this is the structure of benzene. First, there's a ring, but let's look at, there's a ring here. It is cyclic, obviously. Let's look at the 4n plus 2 pi delocalized electron case. Okay, now by now you should know 4n plus 2 pi, where n is the number of rings. So this is one ring. So 4 into 1 plus 2, that should be how many pi electrons? So for a one ring structure, 4 times 1 is 4. I should have 6 pi electrons. So according to Kekule, this, or according to Hooke's rule, for this compound to be aromatic, it should have 6 pi electrons. So let's see if it has 6 pi electrons. Remember, it has a double bond. It has a double bond. So it has a double bond. The double bond, this is double bond, this is double bond, this is double bond. So it has double bond alternating single bond. Now, every double bond, one is a pi bond, the other one is a sigma bond. So for every double bond, one is a pi, one is a sigma. So there are 3 double bonds, meaning we have 3 pi bonds. So one bond is 2 electrons, meaning we have 6 pi electrons in this system. Yes, so this benzene actually has 6 pi electrons, obeying the first part of Hooke's rule, 4n plus 2 pi delocalized electron. But these electrons are not delocalized. Delocalization of electrons tells me that the electrons are not in one region. According to Kekule's structure, the pi electrons are here, the pi electrons are here, pi electrons are here. Delocalization of electron tells me that these pi electrons are everywhere. So that means this pi electron should be everywhere in the carbon. Remember, each of these junctions are carbon. In case you don't know, you're just watching for the first time. It is C6H6. Each of the carbon has an hydrogen. Okay? So if you're just watching, this is it. This is true. So according to Hooke's rule, benzene pi electron should be delocalized, not localized. That means the double bond should be round like this. The double bond should be round like this. So Kekulé structure could explain a lot in Uke's rule, but except for the fact that the electrons in Kekulé structure were not delocalized, they were actually localized. Okay, since they were localized, now we cannot look at the uh, we cannot look at the answer to this. And the answer to this was brought about by Linus Pauling in 1931, an American scientist. By that time, the Americans have dominated the world of chemistry as at this time, unlike the 17th centuries. Okay, by this time they were already dominated. Okay, but this is what Kekulé said. This is what Pauling said. Now, Pauling said something very, very intriguing. Now, Pauling said, if you should take two Kekulé structure or Kekulé and Dewa structure, and you find if you overlay them, if you overlay them, if you overlay them, it will explain that the electrons are actually not. So please, you watch what I say. Okay, this is what I did the first time. Okay, let me do it like this. So if I should alternate this double bond, change the position, it doesn't change. These two compounds are the same, 100% the same. So it means that this double bond can be here, it can be here, it can be here, it can be here. So Paul is now said the average structure of benzene should be this. The average structure of benzene should be this. Yes, this ring actually shows delocalized electrons, where each carbon donates an electron to this delocalized. So each of these carbon and these junctions donate an electron to this delocalized electron. They donate one per electron. So each of these carbon. So this is the resonant hybrid structure of benzene. This structure. So this structure explain why this compound we call benzene is unsaturated and yet still prefers substitution reaction. Yes, benzene is saturated, you heard that, sorry, unsaturated, you heard that right, and prefers substitution reaction. If you've read your alkanes and alkenes, if you have not watched them, if you don't know them, check the videos or that videos. If you watch your alkanes and alkenes, you observe that for an unsaturated compound, you prefer addition reaction because when you add to them, they become saturated. But benzene is unsaturated but prefers substitution reaction because of the extra stability of the ring. So it means that this is Kekulé structure, which is circular hexatriene. This is benzene. And these two structures, somehow, they are a little bit different, but they answer the questions of benzene. This is Kekulé, traditional Kekulé structure. So this is also benzene, this resonance hybrid of benzene. So these are the resonating hybrid. This is the resonance hybrid. Okay, so these are the Kekulé structures. This is the resonance hybrid. So the difference between the energy of this compound and the energy of this compound is around 36 kilocalories per mole. So 36 kilocalories per mole. So the difference between this structure and this structure, or the difference between the energy between this structure. So why this structure is more stable than this is just with 36 kilocalories per mole. And this is known as the resonance stabilization energy. So this energy accounts for the extra stability of this benzene molecule. Okay, having all said that, remember this is just an introduction of benzene. We're going to look at the reactions as time goes on. So it's a very, very long video. So just enjoy. That's what I'm telling you a lot of stories. So enjoy yourself as you watch this video. Okay. This is benzene. This is benzene. Remember, resonance was first explained by Linus Pauling for benzene. This is the resonance hybrid of benzene. So I call it the resonance hybrid. So when you see in your textbook, this is the way they draw benzene in our textbooks. Okay. So benzene in our textbook is ruled like this. So that's for benzene. That's for the structure of benzene. Now, this compound we call benzene has a lot of history, but we will not finish this video if we keep saying those history. It has a lot. So, but I'll quickly move to the physical properties of this compound called benzene. So, what are the physical properties of this compound we call benzene? So, this compound we call benzene, what are their physical properties? Okay, what are the physical properties of this compound we'll call benzene? All right, so physical properties of this compound we'll call benzene. First, All right. So first, the physical properties of benzene. Before I will tell you the nomenclature. So physical properties of benzene. What are the physical properties of benzene? Physical properties of benzene. So this benzene is actually a liquid at room temperature, a colorless liquid at room temperature. So benzene is a colorless liquid at room temperature. That's 25 degrees Celsius. Now it has a melting point. Funny enough, it has a melting point. It has a melting point of around 5.5 degrees Celsius and a boiling point that is around, okay, I say boiling, okay, it's not boiling, it's boiling, okay, and a boiling point of around, it has a boiling point of around 86 degrees Celsius, okay. It burns with a very smoky flame. Now it burns with a smoky flame. This explains that it is unsaturated. So benzene flame is very smoky, which tells us that it's highly unsaturated. So it burns a smoky flame that's a little bit blue in color with some yellow. Okay, it's it it's above 86 degrees Celsius, it can boil and so on and so forth. So those are the properties of benzene. It's highly insoluble in water. Benzene is highly insoluble in water, but soluble in compounds such as ethers, So benzene is soluble in compounds such as, of course, it's an hydrocarbon, C6H6. Okay, so it will not dissolve in water that much, but dissolve in organic solvents such as ethers, toluene, and so on and so forth and so on and so forth. That's for that's for that's for that's for the physical properties. I'll quickly talk about the nomenclature of some benzene derivatives here. So the nomenclature of some benzene derivatives before I come to the properties or the chemical properties of benzene. Okay, the nomenclature of some benzene derivative. So looking at the nomenclature of some benzene compound, obviously some very common ones. I like to just say them. Okay, so if I should have benzene, if I should have benzene, if I should have benzene and I have this, I put OH. No news. This is phenol. This is phenol. Okay. If I have benzene, I put methyl. Methyl benzene. No news. This is toluene. Okay. If I should have benzene and I have something like this, okay. If I put a methoxy group, so methoxybenzene is what we call anisole. So methoxybenzene is called anisole. Some we have benzene, we have amine group, and we call it aminobenzene, or we call aniline, which is used to make dyes. Aniline, benzene compounds. There's so many. When I have NO2 in benzene, I call it nitrobenzene. Yes. So if I have benzene structure, I put NO2, I call that nitrobenzene. If I have a benzene structure and I put um, S-benzene, okay, benzene, and I place SO3H. This what this is benzene sulfonic acid. This is benzene sulfonic acid, not sulfuric, sulfonic acid, benzene sulfonic acid. Okay, I need space, I need more space. If I have benzene, and pardon. So if I have benzene and this is the ring of benzene, and I put so what can I put there? I put CHO. This is an aldehyde. We call it benzaldehyde. Benzaldehyde. Please, it should be noted that benzene itself is highly carcinogenic. If inhaled in as a vapor or in vapor form, this is actually difficult. Though most of its derivatives are most of the derivatives of benzene are not carcinogenic, like phenol. Phenol is not carcinogenic. Toluene is not carcinogenic. Even aniline is not carcinogenic. Okay, but benzene itself is highly carcinogenic. Has belonged to different kind of diseases. Linked to different kind of, you have to be careful when handling benzene. Please, in case you work in the lab, just be careful when handling benzene. Make sure your masks are intact, and so on and so forth. Okay, we have benzoic acid, the guy that is a good preservative. Okay, so when benzene has a carboxylic acid group COOH, it is called benzoic acid. So this is benzoic acid. So remember the ring of benzene. Remember the ring of benzene, and pardon me, the ring is giving me difficult time to draw. So that's benzoic acid. These are the derivative of some benzene structure. So they're on the board, so you can have them to yourself. You can pause the video, go back and draw them. Okay, now for disubstituted benzene, I have to talk about that. Very trivial name for those of us that are beginners, might not really know much about this. For disubstituted benzene, very fast. For disubstituted benzene, that means a benzene that is substituted at two ends. Okay, let's say we have something like this. Let's say we have something like this. Okay, this benzene, and I have let's say NO2, which is nitrobenzene, and I have OH. All right. So there are two names to probably give this compound. This can be called. Please watch. This can be called. Let's call it phenol. So we can call it. So this is phenol. This is one. This is two. We call it 2-nitrophenol. Those of us used to IUPAC name. This should be IUPAC name. Or trivially, we can call it ortho nitrophenol. Let me be done and you see spot the difference. Now, still on orthonitrophenol, another compound with similar properties. Okay, now we have OH here. Now we have NO2 here. If you are good with your math, we call it, this is carbon 1. It should be carbon 1 because guys, the OH, carbon 2, carbon 3. So that should be 3-nitrophenol. So 3-nitrophenol. Now, many of us, trivial names, we call it M-nitrophenol. M means meta position. M-nitrophenol. Now, let's look at another structure for benzene and phenol. So let's say we have this, we have OH, then we have NO2 here. Okay, now this should be 1, 2, 3, 4. You say 1, 2, 3, 4. So this should be 4-nitrophenol, 4-nitrophenol, which is popularly called p-nitrophenol. So p-nitrophenol means para-nitrophenol. Okay, now what does this all stand for? Ortho. So ortho is actually when the benzene or the two substituents on the benzene ring are just adjacent. So like 1, 2. So 1, 2, that's an ortho. When the substituents are 3 apart, so 1, 2, 3, 1, 2, 3. So that's a meta. So this NO2 is meta in position to OH, or OH is meta in position to NO2. Now, when the position is 1, 4 apart, 1, 2, 3, 4 apart, this is para-nitrophenol. So these two are para to each other. So NO2 is para to OH, or OH is para to NO2. So those are for the disubstitution of benzene. There are some other tricks in some naming of benzene. But basically, this is the basis. This is the basis, and this is what this video is all about. This is the basis. So I will try to move to the reactions. of benzene. Try to move to the reactions of benzene. Now, onto the reactions of benzene. Okay, very easy reactions. The reaction of benzene is quite simple. They're just three: addition, substitution, oxidation. When we get into them, you see, they're a little bit more complicated. But let's look at it. Now, for addition reaction, as I said, benzene does not normally undergo addition reaction, except in extreme cases where there is a sunlight, either a free radical attack. But benzene will hardly undergo addition reaction. Benzene prefers substitution as it protects the aromaticity of benzene. Substitution reaction makes it aromatic, or it leaves it in the aromatic state, while addition reaction destroys the aromatic state. Take for instance, now see the first, so this is benzene, C6, H6. This is benzene. Now, if hydrogen is added to benzene in the presence of nickel catalyst, or even palladium as catalyst, what should happen? You observe that the aromatic ring will be destroyed, and we are going to produce a compound such as this. And this compound in today's chemistry is called cyclohexane. So this is cyclohexane, my bad. So this was benzene. You see, cyclohexane is clearly an alkane in naphthene. Cycloalkanes are called naphthene. So this addition reaction is termed hydrogenation. It has destroyed the aromatic nature of benzene. So first reaction of benzene, hydrogenation, the ring destroyed. Now, the next reaction of benzene, okay, taking it off. The next reaction of benzene undergo, it's halogenation. For addition reaction, halogenation. So halogenation is the process, halogenation, process of adding halogens to benzene. Halogenation can be addition, halogenation can be substitution. Now, the most common form of halogenation is chlorination, where benzene is attacked through a free radical mechanism by chlorine. So this is benzene, and it is attacked by chlorine in the presence of UV light. So sunlight provides chlorine radical. There's a mechanism to that reaction. But at the end of the day, you are going to have a compound like this, a compound such as this, Cl attached to each side, knowing fully well that there are hydrogens there. So if I should draw it fully, I would think I would draw that well. So that means what I mean is that there's an hydrogen here. What I mean there's an hydrogen here. That means there's an hydrogen here. What I mean is an hydrogen here. What I mean is an hydrogen here. So this guy is a good insecticide. It's what we call the BHC insecticide. Okay, what is this BHC? Now the name of this compound, first of all, this is benzene. Okay, this is the IUPAC name is 1, 2, 3, 4, 5, 6 hexachloro cyclohexane. So hexachloro, that's the IUPAC name. Hexachloro. So 1, 2, 3, 4, 5, 6. Hexachloro cyclohexane. Now, this guy is trivially called BHC, which means benzene hexachloride. So BHC, benzene hexachloride. BHC is a powerful insecticide. It can kill insects, used in industries to kill, or provided in industries to kill insects. So this is benzene hexachloride, or popularly called 1,6-hexachlorobenzene. So this is under chlorination of benzene. This is one of the common ones. Not all halogens will attack benzene like this. Halogens such as iodine will hardly attack benzene through addition mechanism. Okay, through addition mechanism. But fluorine can. In terms of chlorine, benzene can combust. Fluorine is highly reactive. Okay, but this is a peculiar halogenation or peculiar chlorination that has to do with addition of benzene. So it has to do with addition of benzene. Okay, this is for the common addition of benzene. These are the common addition of benzene: hydrogenation, halogenation. It is difficult to add hydrogen iodide to benzene. It is difficult to add hydrogen iodide to benzene. Now, if some other common guys or hydrogen halide, difficult to add this acid to benzene. Very, 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 very difficult. Okay, very, very difficult. It's not common. If you put hydrogen iodide in benzene, you just keep boiling and you apply it, or in presence of CCl4 as the medium. You keep boiling, and the benzene remain benzene. Okay, so they hardly undergo addition reaction with halo acids. So you even hardly had KMNO4 to benzene. Other things you can add to benzene is now under oxidation. Okay, under oxidation. So the next addition reaction will be under oxidation. So we have to do addition of oxygen in the presence of a catalyst at a very high temperature, or simple ozonolysis of benzene. But I'll look at oxidation as it is linked to addition, just if I look at substitution. So oxidation of benzene quickly. So oxidation of benzene. Oxidation of benzene. Oxidation of benzene ring. Oxidation of the benzene ring. Oxidation of the benzene ring. Okay? Oxidation of the benzene ring. All right. So Oxidation of the benzene ring. So oxidation of benzene. So I'll treat a very simple oxidation, which is combustion. So benzene burns with a smoky flame, which shows it is unsaturated. I did that earlier, meaning it has a high carbon content. If you combust benzene C6A6 in the presence of oxygen, this is burning now. Obviously, there's heat applied. You are going to get CO2 and H2O. Simple combustion reaction. Okay, so if you balance, there are 6 carbon there. There should be 6. Okay, 3. Okay, so let's get the oxygen. Oxygen should be 12. 12 plus 3, that should be 12 plus 3, that should be 15. 15, here should be 7.5. So here should be 7. So 1 mole of benzene equals 7.5 moles of moles of oxygen. So 7.5, so that's 15 also. I repeat, 12, 15. So this is the combustion of benzene. This combustion of benzene. So benzene can burn with a good smoky flame to produce CO2 and H2. If combustion is incomplete, obviously the smoky flame will contain some proportion of CO, carbon 2 oxide. Okay, now the next reaction, next oxidation of benzene is the catalytic addition of oxygen. So catalytic addition of oxygen. Okay, now if you have benzene ring, please, this reaction is very vital and I will urge you to look at it very well. Very vital reaction. If you have benzene ring and you add oxygen to benzene, and about if I'm not mistaken, about 9 molecules of oxygen, and I need 2 of benzene. We'll balance it at the end of the day. So, but you see, so if you add oxygen to benzene, you will obtain what we call maleic acid anhydride. So maleic acid anhydride is something like this. Okay, maleic acid is butyl acid in the cis form. So butyl acid in the cis form. So this is maleic acid anhydride. So you're going to have maleic acid anhydride. Yes, maleic acid anhydride plus CO2 and H2O. I might not need to balance the equation. Okay. Okay, so let's try and balance it. Now, I had 6 molecules of benzene. Okay, in total 12 carbon here. Had 18 oxygen. 18 oxygen, okay? 12 carbon and 18 oxygen, okay? The carbon I have here is 1, 2, 3, 4. 4. Okay, this should be 3 molecules, making it 12 carbon. Or, okay. First, let's balance oxygen, then let's see the remnant of carbon. Okay, oxygen out, 18 out, 18. So let's make this guy 2 first. So this is maleic acid anhydride. This is maleic acid. So my point is, I don't know why I'm stressing you to balance the equation. Okay, I don't know why I'm stressing to balance the equation. It's an organic compound, not an inorganic compound. So, but basically, stress-free. So you can balance offline. If you want me to balance, I'll do a video and balance. You know, we don't want to make this video very, very long. That's the goal also. Okay, catalytic addition of benzene. Let me not forget, at least I forget important things in this reaction, is around 450 degrees Celsius. And the catalyst I'm using is V2O5. So catalytic oxidation of benzene will give me maleic acid anhydride at a very high temperature, around 450 degrees Celsius, CO2 and H2O. Okay, so maleic acid anhydride. And maleic acid anhydride is an acid anhydride. If you dissolve acid anhydride in water, you get the acid. So my point is that if I dissolve maleic acid anhydride in water, okay, if I dissolve maleic acid anhydride in water, I'm going to have something like this. So if I dissolve it in water, H2O, on hydrolysis of maleic acid anhydride, I'm going to have maleic acid. So how does maleic acid look like? I said maleic acid is 6-butyl acid. So 6-butyl acid. So double bond O, have OH, I have OH. Okay, so there's H here, there's H here. If you're wondering why it is 6. So this is maleic acid anhydride. This is maleic acid anhydride. So if I moving the hydrogen, remember the hydrogens at the back there, so no need. So this is maleic acid, this is maleic acid. So hydrolysis of maleic acid anhydride gives me maleic acid, which is butene dioic acid. So you see benzene, it has given us a pure inorganic compound on oxidation. So benzene is a very vast and useful organic compound. Though itself it might be harmful, but it's very important. From benzene you can get a lot. I said benzoic acid earlier. Benzoic acid is used as preservative in industries. Okay. Let me show you something. Let me show you something. Let me quickly show you something. As I just talked about benzoic acid, let me show you something. Okay. Now, still on the oxidation of benzene. So the second reaction we did, you can pause and take the equation. You can pause and take the equation. Okay. You can pause and take the equation. You need them in your exams. It's a very vital video as it's the source of the of information of this video is gotten from so many sources, so many vast sources. So it's very important to your examination, wherever you are, O level, A level. So look at it very well. So now the other reaction of benzene, now let me show you, is reaction with KMNO4. Common oxidizing agent, reaction with KMNO4. These guys, if you know, if you are used to the laboratory work, these guys are conventional with oxidizing agent. There's KMNO4, there's the orange K2CrO2O7, okay, or chromic acid, or any of these guys in acid, okay, any of these guys in acid. So, all right, so if you react benzene with KMNO4, it will shock you to know that there will be no reaction, no matter the condition or the heat. So benzene plus KMNO4, there will be no reaction. So you just boil and boil. Benzene K2CrO2O7, no reaction. That means benzene is unsaturated, yet will not decolorize KMNO4. If you know how to test for unsaturated compound decolorize KMNO4, turn it from purple to colorless. Yes, like the likes of ethene and ethane. But benzene is unsaturated, still will not decolorize KMNO4. Shocking. Very interesting. All right, so to show that benzene does not value the addition reaction as it pertains, as it pertains to other unsaturated compounds. Other unsaturated compounds prefer addition reaction. Benzene don't value that. If I say Brazil, okay. For benzene, if benzene is substituted with any carbon chain at the side, even if this carbon chain is 200 carbon chain, if you oxidize such a compound in KMNO4, in as much as the carbon has hydrogen attached to it, the carbon directly attached to the benzene has hydrogen to it. If you oxidize this benzene in the presence of heat and KMNO4, such compound now is going to be oxidized in KMNO4, such derivative of benzene will be oxidized in KMNO4 to produce benzoic acid. This is methylbenzene. This is benzoic acid. No matter the length of the carbon chain, it will get benzoic acid. My point, if you have such a compound, let's say we have this kind of compound, okay? Let's say we have this kind of compound, pardon me, we have this kind of compound, okay, and we have this kind of compound. This is benzene, obviously. CH2, CH2, CH3. So if you are used to this, this is propyl benzene or phenyl propane. Anyhow, but this benzene compound, this derivative, okay, and you oxidize in KMNO4. You place KMNO4 in such form, K2CrO2O7. This compound will be oxidized on heating to benzoic acid. Now, what is the condition for this reaction? The condition for this reaction is that the carbon directly attached to the benzene ring should have hydrogen. The carbon directly attached to the benzene should have hydrogen which are oxidizable. Yes, you always get benzoic acid. Now, see what I mean? See what I mean? Now, take for instance in this case. So now observe this benzene. Now, this is benzene. Now, but the carbon attached to benzene is a third alkyl. So we have an alkyl group that's a tertiary alkyl group. This carbon is a tertiary alkyl group. So carbons with tertiary alkyl groups, when they are attached to benzene ring, or when tertiary alkyl carbons are attached to benzene ring, they cannot be oxidized. That means if I oxidize this kind of compound, this is third 1, 2, 3, 4, third butyl benzene. Third butyl benzene. If I oxidize this kind of compound, this third butyl benzene, in the presence of heat, if I oxidize this kind of compound in the presence of heat, I will get nothing. I will boil and boil, just like I did for benzene ring. When you eat benzene with chemical, no reaction. So this kind of compound does not get reacted with chemical. Very interesting about benzene. Very interesting. Very interesting. The fourth reaction of benzene I would like to talk about, the number 4 reaction of benzene I would like to talk about is now, or the fourth oxidation I'd like to talk about is ozonolysis. Ozonolysis of benzene. Lastly, ozonolysis of benzene. For oxidation, before we go to substitution reaction, ozonolysis of benzene, before we get to substitution reaction, ozonolysis. Ozonolysis. All right, so ozonolysis. Ozonolysis. If you are watching, it's very interesting. One of the most interesting topics I've jumped on YouTube is this benzene. Now, the fourth oxidation, D, is ozonolysis. Ozonolysis of benzene. Ozonolysis of benzene under reductive workup gives me ethene or ethane diol, which is called glyoxal. What do I mean? Simple. My point is this. I would not like to talk about the mechanism, but I'll just go half step. So I would like to show that benzene, I would like to show benzene from this angle as you understand it better. If this kind of compound should react with benzene, or this kind of benzene, pardon me, should react with ozone in the presence of zinc in reductive workup and H2O, my point, straight up reaction, is that you are going to get glyoxal. Glyoxal is a compound like this, okay? Is a compound like this. What is this compound? Or I would say something like this. Something like C double bond O H C double bond O H. So this compound is ethane diol. That means like ethanol ethane diol, or what we call glyoxal. So ozonolysis of benzene gives us glyoxal. Okay, I would like to show the mechanism, but I will do a special video on this. I will have to beg you guys on YouTube because of time. Because the intermediate of this compound is an ozonide. Let me just show a simple intermediate. I would like to do another video on this, but okay, what I mean is this. If this compound should undergo this reaction, okay, if this compound should undergo this reaction like this, my point is this. At first, on ozonolysis, you're going to produce an ozonide. Okay, you're going to produce an ozonide, which should be like this. Okay, should be like this. First, the single bonds, you're going to get something like this. Okay, O, yeah. Every point where the double bond was, you get an oxygen there. O. Okay, you get O. Yeah, you produce an oxygen first. You get such a compound like this first. An ozonide. This ozonide finds a way to break this ring, and you get this is actually what we call a molozonide. From this molozonide, you get an ozonide. Okay, you get an oxonide. So in the formation of ozonide, this ring must have been broken, and all the way after getting this ozonide, this compound is going to be hydrated on hydrolysis in the presence of zinc. This compound will now give me something like this. Okay, this compound gives me something like this. So let me not just waste your time. I will show you the mechanism in a special video. So if you want the video, just comment in the comment section I want to see the mechanism for the ozonolysis of benzene. I want to see the mechanism. So I'm trying to make it shorter. I'm going to make it shorter. Just show you this is a molozonide, later give it an oxonide, and so on and so forth. So this is for the ozonolysis of benzene. This for the ozonolysis of benzene. The next reaction we have to look at next is substitution of benzene. Yes, the substitution of benzene ring. Substitution of benzene. All right, for the substitution of benzene, I'm going to look at a few reactions very fast, and it will start with nitration. I'll start with nitration. I'll start with sulfonation. Sulfonation. Then I'll start with Fidelcraft. I'll go to Fidelcraft reaction. Fidelcraft reaction. So Fidelcraft reaction. Okay, which other substitution? Okay, I have to talk about. I think I'll start with that halogenation. So when it comes to the substitution reaction of benzene, so I'm going to quickly look at these reactions. Okay, now for them, I'll be very fast with it. I'll start with halogenation. Now, for halogenation, we have a benzene ring. Now we have a benzene ring. If I react this benzene ring with chlorine, usually in the presence of this time not sunlight, I can react in the presence of FeCl3 or aluminium AlCl3 as the catalyst. So any of this as the catalyst, if I react benzene with any of this as the catalyst, I'm going to get chloro or halobenzene, depending on the halogen. So here could be except fluorine. Fluorine will not be able to do this reaction. Okay, fluorine can cause the explosion of or the combustion of benzene. Okay, so except with fluorine. Okay, so if I do this reaction in terms of bromine, chlorine, and what's it called? Iodine. Yes, iodine. Though reaction with iodine is slower. So in terms of this catalyst, the chlorine is going to substitute an hydrogen. Not every of this position in benzene has hydrogen. So you're going to get chlorobenzene plus HCl. So that's for halogenation. Very simple. This should be the catalyst. Okay, this type of reaction is usually termed electrophilic substitution. So the type of substitution benzene undergo is called electrophilic substitution. Let me just quickly explain what happens. So this catalyst, so a little inside of the mechanism, this catalyst, what it normally does is that the catalyst attacks this chlorine first. So when the catalyst attacks chlorine first, we should have AlCl3 plus chlorine, and I'm now going to have AlCl4 minus plus chlorine plus. So the catalyst attacks chlorine, and I have this plus chlorine plus. Now this chlorine plus can attack benzene because benzene is electron rich. So this guy is an electrophile. Okay, this guy is an electrophile. It loves the electron because it's positive. Obviously, it has lost an electron. That's why it is positive. So now it is looking for electrons. So it's an electrophile. So because it's an electrophile, it can attack the benzene ring and find a way to somehow stay in any of the position. So after this guy is going to attack the ring. Yes, it's going to attack the ring, and somehow at first, at the middle, as an intermediate product, I'm going to have something like this Cl, and the ring must have been affected. So I will now have something like Cl minus, and the ring will be positive like this. So in order to get the ring back to, remember, benzene prefers substitution reaction or any reaction that will preserve the aromaticity or preserve the benzene ring. So in order to come back to this state, it has to eliminate this hydrogen. And what can help eliminate this hydrogen? This AlCl4 plus can help capture this hydrogen. So if AlCl4 plus, minus captures hydrogen, so it will capture H plus obviously. When it captures hydrogen, what do you now have? You are now going to have AlCl3 back plus HCl. So we say that the catalyst remain unchanged. So AlCl3 is getting back at the end of the day. So that's why it's called the catalyst. The HCl will be produced as a byproduct. So that's how the substitution or the halogenation of benzene. The same thing occurs for bromination, same thing occurs for halogenation. So in general, this is the halogenation of benzene. So don't forget, this substitution, benzene undergo with substitution mainly electrophilic substitution. So on to the next, okay? On to the next. No time. On to the next. I'll be looking at onto the next reaction. Okay, and the next reaction would be nitration. So nitration of benzene. The next reaction would be nitration of benzene. So how does nitration of benzene look like? Okay, usually benzene is nitrated in the presence. Benzene is nitrated in the presence of nitric acid and H2SO4. So this is benzene. Okay, this is benzene. Just hope you are seeing my benzene. Benzene, and I'm going to react benzene with HNO3 in the presence of H2SO4. So H2SO4. So basically, I'm going to get this is the reaction. I'm going to get nitrobenzene. So this is nitrobenzene. So how does the mechanism look like? How does the mechanism look like? In the reaction, HNO3 reacts with H2SO4, and what I will get is going to be something like, now I'm going to observe, so I'm going to observe a product. So basically H2SO4 and HNO3, this is the mechanism of the reaction. So we're going to basically get NO2 plus H2O plus HSO4 minus. So this guy is the electrophile, the nitro ion. So it is going to attack the benzene ring, just like the way the hydrogen, or rather the Cl plus attacked the benzene ring earlier. So when it attacks the benzene ring, it's going to find a way and get into the benzene ring, okay, and the HSO4 will help to remove hydrogen from the. So when HSO4 minus helps to remove hydrogen from the benzene ring, it remains H2SO4. So H2SO4 in this reaction is more like a catalyst because it chemically remain unchanged. Then then NO2 is going to stay there, and I'm going to have plus H2O as the best. So H2O is the byproduct. So nitrobenzene, H2SO4 remain back at the end of the reaction. So it's quite simple. This for nitration of benzene, I get nitrobenzene. Okay, so there's a little bit of heat in this reaction. So that's how it works. Then lastly, before I talk about Fidel-Crafts reaction, is the substitution that is called sulfonation of benzene. Okay, the substitution that we call sulfonation of benzene. Substitution we call sulfonation of benzene. All right. So for sulfonation, it's quite simple. But I have benzene ring. So this is benzene, and I'm going to react benzene with just H2SO4. So usually two molecules of H2SO4, where one is going to act as the catalyst. One of it is obviously going to act as the catalyst. Okay? One of it is going to act as the catalyst. How? So quickly, this is benzene. Now, how does it act as catalyst? Now, I have H2SO4. H2SO4 reacts with H2SO4. So you must have heard of autoionization before. And I'm going to observe HSO4 minus plus SO3H plus H2O. So what occurred is this. One of the H2SO4 acted as an acid, the other one acted as a base. It's called autoionization. So the H2SO4, this guy that acted as an acid, is going to donate hydrogen. So when he donates hydrogen to this guy, it's going to have HSO4 minus remaining. Okay, this guy received hydrogen and it turns H3. H3 is going to turn H3SO4 plus. So these two together is the H3SO4 plus. So when H3SO4 plus dissociates, it's going to give me SO3H plus and H2. So this is SO3H plus and H2. Remember from our previous explanation, this is the electrophile. So this guy is the guy that can attack benzene, not this guy. So when these guys attack benzene, same mechanism. So therefore, that guy finds a way into benzene, and therefore we're going to have something like this. So benzene, you have SO3H. So what's the name of this compound? The name of this compound is called benzene sulfonic acid. It's called benzene sulfonic acid. So benzene sulfonic acid. So benzene is sulfonated to give us benzene sulfonic acid. So benzene is sulfonated to give benzene sulfonic acid. Okay? Sulfonated to give benzene sulfonic acid. So the next reaction we're going to look at is going to be, the next reaction we're going to obviously look at is now going to be Fide-Krapf's reaction. Fide-Krapf's reaction. All right, Fide-Krapf's reaction. Okay, now Fide-Krapf's reaction. Now this is the last substitution reaction I will talk about if I talk about benzene orientation and dye substitution. Okay, now this reaction is a very unique reaction in organic chemistry, in the world of organic chemistry. It's so important in the world of pharmacy, so important in the world of pharmacology, so important in the world of medicine. Okay, without this reaction, I don't think there will be any compound like paracetamol today. So they would have been paracetaminophenol, which is popularly known as paracetamol. Even there are so many compounds, so many compounds. So that was the most common I could just call. And due to this reaction is so unique, very vast. Okay, now this is a special type of reaction. If you see, I've already explained alkylation, so I'm going to show you acylation also. So this is a special type of reaction in which benzene undergo so somehow the bulk of the compound get into the benzene and substitute hydrogen. Now it's a special reaction for alkylation, acylation, and it's a coupling reaction just to couple two organic compounds. So I have an organic compound like alkyl chloride or alkyl halide reacting with benzene. So I find a way when you couple those two compounds, I'm going to get alkyl benzene. So it's a coupling reaction. Now it's also formylation for formilating. So I have formal chloride. So with benzene, in terms of the catalyst, I'm going to get formal benzene. So this reaction was first carried out by James Kraft and Charles Friedel. So James Kraft and Charles Friedel carried out this reaction. They coupled benzene with an alkyl compound. I think alkyl an alkyl chloride also, and they got alkyl benzene. But why is the reaction unique? Why is the reaction unique? Now the reaction is unique in a way that, okay, if this is benzene now, it has hydrogen everywhere. I just showed one. Okay, react to this alkyl chloride. So benzene with this alkyl chloride. So what do you get? What do you get? Benzene, alkyl chloride. What do you get? Now, what happened in the process is that the catalyst is a Lewis acid. So let me explain the mechanism. Now, somehow, before I talk about the mechanism, the alkyl group, not the halogen, the alkyl group gets and couples with the benzene, and you form, this is benzene, this will become alkyl benzene. So we call it Fide-Krapf's alkylation. As simple as that. That's it. So the catalyst is usually a Lewis-based catalyst, or a Lewis acid, pardon me, which could be FeCl3, AlCl3, or even BeCl2. So these are Lewis acid catalysts that we can use as Fide-Krapf's catalyst. Okay, so what should happen now? Once this reaction occur, the catalyst obviously remove chlorine from the halogen from the alkyl halide. So somehow the alkyl group is now an electrophile. So electrophiles are possibly charged species. Okay, they are looking for electrons. So benzene is electron rich. Should they attack benzene and get something like this? So we have something. So an electrophile has come and collected electrons from benzene, and benzene is that kind of positive, partially positive. So what comes to stabilize benzene? The catalyst, which already removed chlorine and become negative, comes to stabilize benzene. So positive, negative are going to attract. When it comes to stabilize benzene, it cannot get into benzene. So what it does is that this chlorine or the chlorine here have affinity somehow for hydrogen. So the chlorine can remove this hydrogen. The goal is to retain the aromatic ring. So the goal of benzene in this reaction is to retain the aromatic. So since it's coming to remove it, why don't you just remove all the hydrogens? You know the hydrogens here. There's hydrogen here, there's hydrogen here, there's hydrogen here, there's hydrogen here, there's hydrogen here. So why does this guy not remove all the hydrogen? Remember, if you remove all the hydrogen here, it's going to destabilize the ring. So here's the problem. So the goal is to stabilize the ring. So it removes the hydrogen here, and the methyl group remains there. And we have this, then the chlorine that removes the hydrogen form ACl, and we have the catalyst back. So the catalyst is chemically unchanged. So this is the mechanism for alkylation. Okay, now see this one I did here, this simple one. This is benzene, this is ethyl chloride, the presence of that catalyst. So what do you get? So the ethyl group gets into benzene, simple ethyl benzene. Fide-Krapf's reaction. It's that simple. So that what I just did is for alkylation. Now let me look at the craft acylation. For acylation, I have Fidecraft's reaction by God's grace. Okay, Fidecraft's acylation. Now I'm going to react on acyl chloride. Acyl chloride are usually alkanoyl chloride or alkanoyl halide. So when I mean alkanoyl, like we have an alkanoic acid. So when the hydroxy group in the alkanoic acid, alkanoic acid have hydroxy and carbonyl group together as its functional group. So when the hydroxy group is replaced with chlorine, it becomes acyl chloride. So this group, note it, this group CH3CO plus is an acyl ion. So that's an acyl ion, or we call it an alkanoyl ion. So this is an alkanoyl group. So alkanoyl. So alkyl carbonyl. So that's where it comes from. Alkyl carbonyl, alkanoyl, acyl, alkyl carbonyl. So that's where it comes from. So we have benzene reacting with this acyl chloride is called ethanoyl chloride, or we call it acetyl chloride, acetic acid chloride. So acetyl chloride. So acetyl chloride reacts with benzene. So what should you get? Now remember the catalyst. The catalyst is usually AlCl3. So what happens is that the catalyst find a way to create, if you follow this mechanism, try a way to create this electrophile. So this electrophile is going to attack benzene. Any of the position is position 1. So what you get now is going to be COCH3. So the name of this compound, I like to draw the name of this compound. Please don't look at this compound very well. This compound is known as acetophenone. Acetophenone. This acetophenone. So benzene plus acetyl chloride, I'll get acetophenone. It's an aromatic ketone, so it is called phenones. Aromatic ketones are called phenones. So why is it aromatic? Because the carbonyl group, this CO group, is bonded to the benzene ring. This CO group is bonded to the benzene ring. So we normally say that the Craft's acylation is used to produce aromatic ketones. So the Craft's acylation is a reaction used to produce aromatic ketones. It's so simple. This is basically Fidecraft's acylation and Fidecraft's alkylation. So it's this simple. So I can try another one. So should I try? Okay, let me just give you a simple Fidecraft reaction. So the one I'm not talking about is formylation and co. Okay, in subsequent videos when we're looking at phenols, we'll see that. So we have CH3CO. Okay, CH3CO, or I'll say CH3CH2COCl. Okay, so what should be, remember the catalyst is AlCl3. So what should be my product now? My product now is now going to be, so let me write my product here somewhere. So assuming I have this reaction, okay, you try this instead of giving you everything. So the catalyst is AlCl3. So on AlCl3, what will be the product? So you write the product in the comment section. So when you get it, you write the product in the comment section. If you cannot get it, I'll do a video to also explain. So now I'll be looking at dye substitution and orientation of benzene. Dye substitution and orientation of benzene. Dye substitution, orientation of benzene. All right, for that substitution of benzene, it's kind of tricky, but I will have to talk about two things. So the first thing I'll talk about is what we call ring activators. So there are some substances or some group that can activate benzene ring, and there are some substances or group that can deactivate benzene ring. So I'll talk about ring activators and ring deactivators. So ring activators and ring deactivators. Now, first, what is a ring activator? A ring activator is a group that is actually a electron donating group. So benzene is electron rich. Any group that can donate electron to benzene can usually protect the aromatic nature of benzene. So they activate the ring. So electron donating group are ring activators. What are ring deactivators? Ring deactivators, though difficult, but they can, are electron withdrawing group. This electron withdrawing group are what's it called? Ring deactivators. They usually have unsaturated centers. So in such group, there's one or more double bonds. So in such group, there are one or more double bonds. While ring activators are usually have saturated centers, so they don't have double bonds in such groups. So this group, let me list them, and I'll tell you how they activate and deactivate the ring. So for ring activators, we usually have OH, we usually have NH2, we have the alkyl group, common guys, we have the amine group, okay, two, the amine group, and so on and so forth. Now for ring deactivators, we have NO2, electron withdrawing group, we have SO3H. Okay, if I draw the structures for you, I think you get NO2 is best drawn like this. Okay, it has one or more double bonds, so unsaturated center. So SO3H also sulfonic acid group. So I think SO3H is drawn like this. Okay, I'm not thinking, but it is drawn like this. Okay, OH, and I think double bond O. So and there's a positive charge here somewhere. So there's a positive. So NO2 plus SO3 plus. We have um, CO, the carbonyl group, C double bond O. We have CHO, C double bond OH. We have CHO group. We have name it, any group usually with unsaturated centers that can attach to benzene. Usually, so we have the carboxylic acid group also. Yes, so these are ring deactivators. Why do we call them ring deactivators? Why do we call them ring deactivators? Okay, now quickly, ring deactivators, this video will be very helpful for those of us still entering organic chemistry in the A-level days. I mean 100 level, 200 level, even some 300 level students also need this also. But quickly, ring activators um, usually now I have benzene calculate structure. Back to the start of our video. Now calculate structure. Pardon me, my benzene is somehow. Okay. Now this benzene ring is usually, I told you the electrons are delocalized. Delocalized. Okay. Let's say I have NO2 in this benzene. So NO2 in benzene. So obviously there will be resonance though where the double bond. Now what happens in this benzene? What happened? Now, if I have NO2 here, okay, I think I should use calculate structure to explain. It will be easier for you to understand with calculate structure. It will be easier for you to understand with calculate structure. So I have NO2, double bond O, O. So my double bond should now be somewhere here. My double bond should be somewhere here. My double bond should be somewhere here. So somewhere. Now, this is NO2 on benzene. So this is NO2 benzene, so nitrobenzene. So what happened is this NO group is electron rich and have the ability to maintain this N2O because NO2 already should have resonance. That means there should be somehow the double bond distribution is not equal. So let me put that here. So the double bond distribution in NO2 is not equal. So I'm supposed to have something like this. NO. So with resonance, I can also have something like N. So I have the positive on here. I also have the single bond here, double bond O. Yeah, so resonance can occur. So, but somehow, to maintain the ring, to maintain this double bond, it withdraws electrons to itself from the benzene ring. So withdrawing electrons from the benzene ring, what does this carbon do? This carbon in turn try to withdraw from here. So when this carbon tries to withdraw from here, it creates a kind of positive charge here. So it has activated a position. So if you are used to benzene at the beginning of this class, we said for benzene, when it is, let's say OH and OH, when these two OH are 1, 2 to each other, they are next to each other like this, 1, 2, we say it is auto. So this position called the auto position has been activated. So it's going to, so this NO group activates, pardon me, my bad, since it withdraws electron, that was wrong of me, since it withdraws electron from it, so it's going to withdraw from here. Now, After withdrawing from here, it is observed that this guy and this guy still have the double bond. So that was wrong of me. This guy and this guy still have the double bond. Now, when it tries to withdraw from here, it activates this position. So somehow the resonance occurs like this. So this position is activated. So it occurs for every electron withdrawing group. So this electron withdrawing group is said to be a metal director. So this is 1,2 is auto, remember? Then 1,4 or 1,3, pardon me, is metal. So 1,3 metal, 1,2 auto. So 1,3. So it activates it. So these ring deactivators are usually known as metal directors. They are called metal directors. Why? To cut the long story short, the ring activators are known as auto-para directors. Okay, so they activate benzene at auto-para direction or auto-para position. So they activate benzene ring at auto-para position. This one is deactivate benzene ring but activates the metal position. They deactivate benzene but activate the metal position. Why these ones are auto para directors? Now, but there's an exception. Now, the halogens, chlorine, bromine, fluorine, these guys are not having unsaturated centers. They are electron withdrawing group. These guys are electron withdrawing group. We call them minus I group. We call them minus I group. So this minus I group are supposed to normally deactivate benzene ring, but somehow they behave like ring activators, but they are electron withdrawing group, but they behave like ring activators. So this minus I group, though they are electron withdrawing group, they are also ring activators. They are ring activators. It's not really, they're not really ring activators. They actually deactivate the benzene ring but activate auto para position. So that's their major characteristic. So we call them auto para directors. So these guys are auto para directors. This electron withdrawing group. So the only electron withdrawing group that are auto para directors are the halogens. Okay, they're the halogens. The sole reason is because the halogens can withdraw electrons. They withdraw electrons, and their pool of electrons is usually not as strong as these deactivators. Okay, these other deactivators, they are not their pool, so they are usually bad. Let me use the word bad electrophiles. If they can act as electrophiles or they love electrons, they're usually bad electrophiles. But they deactivate the ring to a very small extent, but they are autopara directors. Autopara directors. So having known that, we can look at our substitution or that substitution of benzene. So these two concepts is so important. Very, very, very important. So I'd like you to look at it, let it dissect, let it digest it. It's a very long video for benzene. Should be almost 1 hour up. All right, so we have a reaction on the board, and this is nitrobenzene. So you normally can ask this question in word form, depending on your exam. So this is nitrobenzene. Okay, now nitrobenzene is going to be methylated. So this whole reagent is a methylating agent, whether you like it or not. We already saw it. Now, when nitrobenzene tries to react with alkyl chloride in the presence of aluminum chloride, if you remember this reaction, this is a Fidecraft alkylation. Okay, this is a Fidecraft alkylation. So what should happen is, this is not just benzene again, this is nitrobenzene. So benzene already had a substituent in it already. So now another substituent is going to enter into benzene, but this substituent is methyl. This is Fidecraft alkylation. Remember, it's producing this alkyl group. So this alkyl group is going to enter into the benzene. Now, if the alkyl group is going to enter into the benzene, this NO2 is going to direct the alkyl on where to go. What did we call it earlier? It's a metal director. So it's going to direct this methyl group not to attack here, not to attack here, but to attack the third position. 1, 2, 3. So it activates the ring at this third position. So we call them metal directors. Okay, so and we will say it increases the electron density at this particular point. So to increase the electron density at this particular point, so that you can attack these guys. Okay, so what happened? Okay, it activates this position, and what do you have? We're going to have something like this is nitro group, and we're going to put methyl here. Okay, so it makes this electron density here, it increases it. There'll be kind of a scarcity of electron here. Why these other ends we're going to have electrons? So, but somehow, NO2 is going to direct metal to the metal position. So, what we're going to have is going to be metal nitro, metal nitro. Okay, remember nitro, metal benzene is called toluene. So, metal nitro toluene, or people can say metal methyl nitrobenzene. Anyhow you see it. So another one I'll try to also give you. So they have skill of sulfonation. So let's say sulfonation of let's use chlorobenzene for instance. So if chlorobenzene should undergo sulfonation, so how does sulfonation look like? Remember, sulfonation is a reaction with H2SO4. So once this benzene, any benzene reaction you know sulfonation is about to occur. So sulfonation is about to occur, and sulfonation. So how does it look like? So this is, so pardon. So this is my, okay. So sulfonation is about to occur. Okay. Now, but what group is chlorine? Chlorine is actually a para director. Auto para director. We said that earlier. So what chlorine will direct this guy to either the auto position. This is auto. This is meta. This is para. This is meta, yes, this is auto. So it's going to direct it to the auto. So somehow we're going to produce a compound like this. We're going to produce a compound like this, ClSO3H. So we're going to have we're going to have chloro benzene sulfonic acid. But what chloro? Auto chloro benzene sulfonic acid. Benzene sulfonic acid. Auto